All right, so I'm in this section's chair. I'm Kai Chiu from RIKEN-iTHEMS. So today we have invited Hamazaki-san from also RIKEN. What's PRI?
Oh, pioneering research.
Oh, pioneering researcher. Yeah, he's a team leader. Hakubi in Chinese is Bai Mei, means a very smart person, and he has some very famous paper for the NAF mission, many-body localization. So, yeah, it's like the previous talk, like many-body localization. Okay, so let's welcome him to give a talk.
Yeah, thank you very much for a kind introduction. And first of all, I'd like to thank the organizers for giving me this great opportunity to talk about our recent work. So my name is Ryusuke Hamazaki from RIKEN, and today I'll talk about our work on measurement-induced spectral transitions and measurement-induced statistical crossover based on these two papers, which are done in collaboration with Ken and Kazuki, respectively. And I recently wrote a review paper on like measurement-induced measurement-induced physics with Ken, Hisanori, and Yohei. So if you're interested, please look at it. Okay, so here's the outline of my talk. And first of all, I'd like to give a kind of very general introduction and motivation of my research because there are people in the audience from different backgrounds. And then I'll talk about two topics which are related with measurement-induced many-body physics. Okay, so let me start with the introduction. So in physics, there are two pillars. And one is quantum mechanics, which describes microscale, like dynamics of atoms and molecules. And the other is thermodynamics, which describes macroscale, like temperature, pressure, volume of solids or liquids. And the theory that bridges these two topics is statistical mechanics. And if we especially consider equilibrium statistical mechanics, then the thermal state is given by Gibbs ensemble like this. But my goal of research is to go beyond such equilibrium states and consider far from equilibrium dynamics. And although there may be a lot of approaches to go beyond equilibrium, my approach is to start with the quantum mechanics and what kind of universality of non-equilibrium many-body dynamics emerges. And actually, this type of trial to bridge quantum mechanics and statistical mechanics has a long history, which dates back to von Neumann's seminal paper in 1929. So he wrote a paper in German like this, and here are H theorems correspond to the so-called Boltzmann's H theorem, which is a seminal work in classical non-equilibrium statistical mechanics. And here, neue Mechanik means a new mechanics in English, and this corresponds to Schrödinger's equation of quantum mechanics in 1926. So this means that, interestingly, only 3 years after Schrödinger's equation, von Neumann considered a very fundamental problem of bridging quantum and statistical mechanics. And what he actually did was to try to derive equilibrium statistical from quantum mechanics, which is now known as a problem of thermalization in isolated systems. So in particular, he started with some non-equilibrium states, say a system, a gas of particles which are confined within the left half on this box. And then if we remove the wall in the middle, we know that as the final state, the state is described by the Gibbs ensemble or thermal ensemble, but he tried to kind of derive it only from a Schrödinger equation of quantum mechanics. But now this type of investigation of non-equilibrium quantum many-body dynamics has attracted a lot more attention in recent decades, and this is because of the development of quantum simulators and quantum computers, which are also explained in the previous talks. And in particular, these systems are physically constructed from from cold atomic systems, superconducting qubits or trapped ions. And importantly, these can realize noiseless systems with extreme controllability. So this means that we can tune the microscopic parameters of the Hamiltonian relatively freely, which cannot be done for usual material, conventional materials. And in fact, because of this high controllability, these quantum simulators and computers now provide us a platform to investigate non-equilibrium physics from quantum mechanics. So, for example, this example shows verifies thermalization of isolated systems using cold atomic systems. But you see that this is just this is a result 10 years ago. But now we can investigate more complicated non-equilibrium dynamics using these quantum platforms, like the so-called out-of-time model correlators, which are hidden correlation unique to quantum mechanics. Or we can also now verify the dynamics of coarsening or surface growth, which are originally known in classical many-body systems, but they consider it under quantum many-body fluctuations. So this means that non-equilibrium quantum many-body dynamics has become the frontier of modern quantum science. But now, in this talk, I especially want to investigate the physics of open quantum systems. And so let me explain it briefly. So isolated systems are systems with no external environment. And then, as I said previously, these systems typically reduce to thermal equilibrium states, which are kind of trivial because the entropy is maximized. But open systems exchange like energies or particles with the external environment. And then this means that the dynamic is no longer described by this Schrödinger equation. So this means that we may find non-equilibrium phenomena richer than those in isolated systems. So that's why I want to talk about open systems here. And actually there are two ways to realize such open systems. And one is just to attach, for example, heat baths to induce dissipation. And the other is a quantum measurement where a system is attached to external measurement apparatus. So in quantum theory, quantum measurement is regarded as an open system because this measurement apparatus can be regarded as an external some environment. And actually these two are a bit different. And for the case with heat baths, systems information will be lost in time. So this means that the initial pure states of the system are eventually mixed after a long time. So this is kind of simple. In contrast, if we consider quantum measurement, systems information is stored as measurement outcomes. So this means that unless discarding measurement outcomes, initial pure states remain pure. So this is kind of interesting because we can utilize such information of the system obtained from the measurement. So actually this quantum monetary system lead to kind of richer physics compared with the just heat bath case. So I'm going to talk about this quantum measurement here. And in particular, what I will discuss today is monitored many-body dynamics and their universality. And actually, quantum simulators and computers now enable us to perform even quantum measurement during many-body dynamics. So here, mathematically, quantum measurement corresponds to non-unitary effect, meaning like this, whereas unitary effect corresponds to, many-body dynamics corresponds to the unitary effect. And actually, because of the competition between these two effects, we expect novel non-equilibrium phenomena unique to monitored many-body systems. And one of the most famous ones is the so-called measurement-induced phase transitions. And as I'll talk about it, although I'll talk about it in detail, I'll explain it a little bit here. And this, for example, this paper considered quantum computers or quantum circuit and add some measurement during many-body unitary gates. And then they find some interesting phase transition of the entanglement entropy if they change the frequency of the measurement. And so then today's topic is to find out some universal principles that characterize such many-body systems under measurement. Okay, so that was the introduction. And now I'll talk about the main part. And the first topic is what we call measurement-induced spectral transition. And here we ask whether phase transitions in non-equilibrium open systems can be understood within the same framework as those in equilibrium systems. Okay, so before talking about my result, let's consider how quantum measurement can alter the entanglement of a system. So entanglement is a kind of correlation unique to quantum systems. And if we consider, for example, many atoms or many qubits, then the interaction between them increases the entanglement in time. So this is a unitary effect. But in contrast, it is known that measurement, which is a non-unitary effect, decreases the entanglement of a system. In particular, if we, for example, look at a particular atom or qubit, then this kind of collapses the wave function and then kills the entanglement surrounding to it. Okay? So this means that there will be a competition between interactions and measurements on the entanglement structure. And actually, these papers found that there's a transition due to measurement and interaction. So they especially consider a quantum circuit realized on a quantum computer, and by they consider interaction which increases the entanglement, and also the measurement which decreases the entanglement. And then they ask, what is the entanglement of the long time state, psi t? Okay. And what they found is that there is a transition as a function of the measurement strength. So in particular, if the measurement strength is weak enough, the long time state, the entanglement of the long time state grows with respect to the system size. So this is an entangled phase or volume law phase. And but if we increase the measurement strength, then there will be a transition, and we enter the non-entangled phase or area law phase, where entanglement is just constant with respect to the system size. And as I said previously, these measurement-induced phase transitions are experimentally realized on a quantum computer. Yep. Yeah.
Is the monitored measurement in the selected one, for example, safety outcome, or just the measurement? Which type of
Okay, so they consider one specific measurement. I mean, set of one set of measurement outcomes. So if we average over it, then we cannot see this phenomenon. So if we keep track of the measurement outcomes without discarding it, then we find this type of phase transition.
Can you measure the entanglement and you do a measure that is the entanglement
I think they just considered tomographic measure. I mean, so okay. So this is a so if we know the reduced density matrix completely, then they can measure the entanglement, right? Yeah. And actually, there are different ways to measure entanglement in quantum simulators. Some clever ways, but I think they used just a tomographic measurement, if I remember correctly. But anyway, entanglement is also kind of measurable, although the cost of measuring it is not so low.
And doesn't this behavior depend on what kind of measurement?
Okay, so this is here I showed the simplest case where we consider unitary dynamics and a single measurement in the sigma z direction. But we can consider different type of measurement, like non-commuting. Yeah.
Type of measurement. In that case, where things doesn't
Actually, right, but that's true. And if we consider bell time measurement, then they create a certain measurement. That's true. And actually, there are some studies considering such bell type measurement. And then, for example, if we consider non-commuting measurements, the transition can occur even without unitary dynamics. And yes, there are some studies on that. So any other questions? Okay. Yeah, so this phenomenon is called measurement-induced phase transition, or MIPT for short. And this MIPT has attracted a lot of attention in recent years because it's regarded as a unique type of phase transition occurring non-equilibrium open systems. But still, it is not so much well understood about what are similarities or differences between this MIPT, non-equilibrium open systems, and more conventional quantum phase transition in isolated systems. So that's what we ask. And for this purpose, let me first briefly review what was the quantum phase transition in isolated systems. So this is a transition where the properties of the energy ground state change drastically. So if we consider many-body Hamiltonian and diagonalize it, we can define energy eigenstate with the minimum energy, and this is a ground state. And if we change the external parameter of the Hamiltonian, such as magnetic field strength, then we'll have phase transition. And for example, entanglement transition actually occurs. And for typical, for example, 1D critical systems, we have two phases, which one is an entangled phase, and the other is a non-entangled phase, right? But now, in this case, there's another type of interesting transition known as a spectral transition of the energy gap. So energy gap is defined as a difference between the ground state energy and first excited state energy. And then if we change the parameters, we have two phases. One is a gapless phase, where this delta H vanishes in the thermodynamic limit, like this. And the other is a gapped phase, where delta H remains constant even in thermodynamic limit. And most interestingly, these gapless gapped phase transitions and the entanglement transition coincide for this isolated system case. Okay. And now our result is to extend this universal relation between entanglement and spectral transition in isolated systems to non-equilibrium measurement-induced phase transitions. So that's our main claim. So this means that there's a spectral transition due to measurement. But here we find an apparent difficulty because time evolution of a monetary system cannot be described by a usual Hamiltonian. In fact, if we consider time evolution of this psi t, then it's described by like this, where Vt of omega is a non-unitary operator which depends on random measurement outcomes, omega. So omega is a set of, like, for example, plus or minus. And this means that this time evolved state highly depends on measurement outcomes, and they kind of create spatial temporal disorder, right? So this is unfavorable, and it is highly non-trivial how we can find some spectral quantity independent of the random measurement outcomes, omega. But now, to overcome this, our idea is to focus on the so-called Lyapunov spectrum of the non-unitary operator Vt. So this is originally a concept known in classical chaotic systems with many degrees of freedom. So if we consider usual classical chaos, then if we part of the phase space, then its distance will grow exponentially in time, and its rate is usually known as the Lyapunov exponent. But Lyapunov spectrum is a kind of high-dimensional version of this. But now we use it, we apply this to this monetary quantum many-body dynamics. And in particular, if we consider a long time limit of a quantity which is proportional to the logarithm of the singular values of this Vt, then it converges to values which are independent of measurement outcomes. So this is a Lyapunov spectrum. So I skipped the detail, but the point is that this independence of measurement outcomes, which is very suitable for our purpose, and then once this Lyapunov spectrum is defined, we can define the Lyapunov spectrum gap naturally as a difference between the smallest Lyapunov spectrum and the second smallest Lyapunov spectrum. So this provides an analogy with the gap in isolated systems. And then we ask what happens when the measurement strength is varied. And here's the result. And so this is a thermodynamic limit of this Lyapunov spectrum gap as a function of measurement strength, and we find a clear transition from a gapped place to a gapped phase. And actually, we also find that the transition point is coincides with the entanglement transition. So this means that there's a universal relation analogous to ground state transitions in MIPT. This means that for both cases, entangled phase corresponds to a gapless phase, and non-entangled phase corresponds to a gapped phase. Gapped phase and entangled. Okay. If we consider, I think, locally interacting systems, then gapped phase means that small entanglement. Yeah. In our case, we do not find any examples, any counterexamples yet. So actually, we tried several other types of circuits, but they are kind of true. Yeah, of course, we need to be more careful about like scaling, like whether the gap is polynomially or exponentially decaying, or entanglement is volume law or logarithm law. But still, we find that this seems to be universal, at least. So does it answer your question? Or? Okay.
So far these states are all pure states.
Right. Yeah. Okay, so yeah, so first of all, as Iso-san asked, we consider a case where the measurement outcomes are not discarded. So we always keep measurement outcomes. So we track quantum trajectories. And then in this case, if we prepare an initial mixed state, they can prepare it. And finally, we can discuss the dynamics in the pure state language. Yeah.
Would you say compare numerically, or is that one rigorous?
Oh, it's a numerical thing. Yeah.
And do you do any system size scaling?
Okay, so this is kind of a interpolate. Yeah, so from numerics, we interpolate the thermodynamic limit, and then we find this. So in that sense, we kind of perform finite size scaling. And actually, for the gapless phase, in this case, the gap exponentially decays with respect to system size, which is kind of very, which is not so typical for usual isolated case.
Are there any particular exponents that we can extract from?
Yeah, actually, we try to do that, but yeah, it's difficult to find it. Yeah, thank you. Okay, so we considered like system size scaling, and for example, in this simple case, we entanglement phase in the entanglement phase, the entanglement entropy of a subsystem increases with respect to the system size or subsystem size. So this is a volume law. But for the non-entanglement phase, it does not increase. So we numerically find it. And so this was known before, but so yeah, so that's our way to do one of the ways to do that. Okay, is okay. Yeah. Yep.
Yeah, so this epsilon is a Lyapunov exponent of, sorry, what?
Okay, Lyapunov exponent of the time of evolving operator. So the time evolution is governed by this non-unitary operator, and the Lyapunov exponent of this time evolving operator.
Yeah, so the expansion between gapless and the gap phase means where, usually where we use the Hamiltonian spectral activity. So what does this mean?
Oh, so this, so usually Hamiltonian is fixed, but we change the parameters of the Hamiltonian, right? And then there's a phase transition. No. Even for time-independent case, if we change the parameters like magnetic fields, then there will be a phase transition. So, but instead of changing parameters, we here change the measurement strength. And then we have no spectrum changes our gapless gap transition.
If parameter is changed, then usually Hamiltonian is so of course there are the spectral. But in this case, measurement, the strength of measurement changes. What does it mean?
Sorry, I didn't explain that. But for example, one way is, for example, in this paper we considered measurement which consists of some error in the measurement. So if we consider errorless case, then we find out just measurement is a projective measurement. But if error is maximized, then it just does nothing. And then we can continuously change the strength of the measurement. So this is reflected in the cross operators in each of the measurements. So it's an external parameter. So I did not write that, but this explicitly depends on the external parameter as a measurement strength as an external parameter.
So in the sense of the Lydian operator,
Mm-hmm.
so that the Lydian operator is different depending on this the measurement.
Yeah, actually, this is a kind of not a Liouvillean, but that's similar. So this is a kind of post-selected quantum trajectory. So this is not a Liouvillean, but yeah, it's similar. The concept is similar. That's similar, related. Yeah. Although this is more difficult than non-Hermitian because we take into account each of the measurement outcomes which are kind of all discarded in the non-Hermitian case.
So the value is independent of the omega?
Yeah, that's true. So that's highly non-trivial, but it's shown mathematically.
The fact that it's independent is
Non-trivial.
non-trivial.
Yeah, because we consider Born measurement probabilities. So if these measurement outcomes are independent, then we can show it, although it's a bit complicated, too. But since we have this probability of finding some measurement outcomes kind of depends on the previous quantum state, then this independence of measurement outcomes is much more harder to prove. But it has been proved by mathematical physicists. Yeah. And finally, I'd like to mention that this spectral transition actually has some physical meaning of a transition in the relaxation time. So this is kind of a spectral theory of MIPT, and so we have extended the framework of equilibrium quantum phase transitions to non-equilibrium systems. And actually we have some, as a following work, for example, we discovered that the so-called Barclay correspondence, which is originally known in equilibrium phase transitions, can also appear in the measurement-induced topological transitions. Okay, and I don't think I have time to talk about the second part. Maybe I just skip this, all of them. Okay, so here's a conclusion, and yeah, I wanted to discuss universal non-equilibrium phenomena in quantum many-body systems under measurement, and we especially found a spectral transition from gapless to gapped phases upon the entanglement transition of a monitored circuit. And yeah, so I was not able to talk about the second part, but yeah, this is about trial to find a measurement induced interesting many-body universality without the so-called post-selection problem. And yeah, actually we find some interesting anomalous universal scaling of some fluctuation of the quantum jump trajectories. But so if you're interested, please ask me anytime. Okay, so thank you very much for your attention.
Let's take a few questions.
Yeah, so this very non-standard phase transition can be described in terms of some kind of minimization group, or where you talk about this normal universal scale. So I wonder whether there is any universality.
Yeah, for the case of actually this is a bit different from MIPT, and I don't know the origin of this anomalous scaling here yet, precisely. But for this case, yeah, actually, as previous works which are not ours, there's a trial to consider some universality of MIPT using some field theory or normalization group, and yeah, so.
So is that non-Hamiltonian type normalization group, or what's So quantum process where you first select the measurement outcome. So the system goes in a non-Hamiltonian way. That's not correct?
Right. So yeah, yeah, but yeah, at the level of like quantum. So they consider measurement outcomes. So it's not treated as the usual simple non-Hermitian matrices. So they kind of consider some replicas to make it analyzable using field theory theoretical method. And then, yeah, they discuss such like origin.
There is no classification theory, like where the ordinary, conventional universality.
Yeah, there's kind of some kinds of classifications, but yeah, there are many types of classifications, so they are not classified. Some like for topological case, measurement-induced topological systems, there's some work on classification, and also, yeah, actually MIPT, the critical point of the MIPT is kind of regarded as a non-interactivity, but I don't think there are some trials to, justify that, but I don't think there are, conclusive results for that. But there are many trials for those approaches.
Last question.
Yeah, actually, that's also a very good question. And actually, the answer is they differ. So, for example, if you consider like some, I forgot the name, max Rayleigh entropy. No, I don't know. So some kind of simplest any. So, for example, Hartree entanglement entropy. Then we find analytically that the phase, the transition point is like 1/2, and also, I mean, there will be a CFT there. But for the entanglement entropy, the transition point also differs, and the criticality will also be regarded as different. So, and yeah, it's in a sense annoying, because if we use different quantities, then these criticality or phase transition points differ. But it's at the same time kind of interesting, because if we consider nonlinear quantities, we can find interesting. Yeah. Uh-huh. Oh. So you say that even for equilibrium systems, you yeah. Mm-hmm. Mm-hmm. Oh, that's true. Yeah, that's true. Yeah, I agree. I agree. Yeah, that's true. I didn't consider that point actually, to be honest. But yeah, I think it's interesting, and at least the usual von Neumann entanglement entropy seems to coincide with the gapless gap transition at numerics. Yeah.
Right. Let's thank speaker again.
Yeah. Thank you very much.